Okay, so like we just derived here, we have these two equations. An equation for resistance in a wire, and you can see that in the blue, and Ohm's law, which relates voltage, current, and resistance all together. It is important to note here that Ohm's law only works for ohmic devices. So like resistors obviously are ohmic devices. And what I mean by an ohmic device is that when you increase the voltage, your current increases proportionally. So not all devices do that. So eventually we get to chapter 32, when we talk about AC circuits, we'll see some devices are don't quite follow this. Okay, so really important equations here. What I want to do now is start applying these to examples and to start looking at circuits. All right, so let's do that here on the next page. Okay, so we haven't seen circuit diagrams yet. So I'm going to draw a circuit diagram. And here's kind of how a typical circuit diagram looks like. You have a battery, right? Something that provides voltage, and that's what batteries do. So let me go to a different color. Okay, so the battery, I think we have done a battery, but just in case we haven't, you have a long line, right, representing, I think we did, representing a higher voltage, and a shorter line representing the lower voltage. Okay, so this would be the positive end of your battery, right up here. And this will be the negative end of your battery. Okay, so these batteries are connected by wire. So you have a wire coming out the positive side, going down and going to some resistor. And the way we model resistors in a free body diagram, or not free body diagram, in a circuit diagram is like this. It's kind of like this zigzag, jagged kind of thing. Okay, so this is my resistor. This battery provides a voltage. Okay, and the current comes out of the positive end, goes towards the negative. So one thing to remember about current, and I mentioned this earlier, but it's so important that I'm going to write it out. Current always goes from higher voltage to lower voltage. So we're going to have current going this way. Okay, so let me put that here. So current flows from higher voltage. Remember, we're looking at when we're talking about current, we're looking at the flow of positive charges. Okay, so that's my circuit diagram. It's worth noting, we have done circuit diagrams. Just remember what we did with capacitors. Remember that, let's say that anywhere along this wire, so like I said, current goes from the higher voltage to lower voltage. So the long line here, this arrow, this longer line of the battery, that represents a higher voltage. This represents a lower voltage. Okay, maybe you're thinking that it could just go from higher to lower like that, right? It can't do that. Batteries don't work that way. Batteries only, they take charges from the lower end and increase their energy and put them out on the upper end. Okay, this is the higher potential, so it's going to go from the higher potential down to the lower potential, which is this part here. Okay. I'm going to explain it in a different way right now, but hopefully that makes sense. Okay, so let's say this is let me just put a number here. Let's say this is 6 volts battery. So I'm just going to say 6 volts here. So it'd be 6 volts, yeah, no problem. 6 volts there, and then on the bottom, that's going to be my 0 volts. Okay. So anywhere along this wire, we still have that what we said about conductors. Anywhere along this wire is pretty close to 6 volts. Right? I have all these 6 volts there. Okay, on the bottom part of the wire, anywhere along this wire, Right? Anywhere in that wire, you have 0 volts. Okay, so a lot of your voltage drop, right, what takes away the voltage is from the resistor. Okay, now in reality, these wires do take out a small amount of voltage. So maybe it starts off at 6 volts by the battery. By the time it reaches a resistor, maybe it goes down to like 5.9 or something like that. Okay, so these wires do take a small amount of voltage, but the majority of the voltage is going to come from the resistor. Okay, so anyway, so all that voltage, like we could let's give some numbers so we could do a small calculation at least. So let's say this is a, I don't know, a 3 ohm resistor here. Okay, so if I think about Ohm's law, right? Ohm's law is your voltage drop across your resistor equals your current going through the resistor times the resistance. Okay, so let's say I wanted to find current. Okay, I'll just rearrange Ohm's law. Okay, rearranging Ohm's law, and I had to ask myself, okay, what is a voltage drop across a resistor? Okay, now you don't have to put a negative here because that delta V is already understood to be voltage drop, so don't put a -6. Okay, the resistor, the resistor experienced a voltage drop of 6, right? It goes from 6 volts to 0 volts. So I'm gonna put 6 volts here. And then the resistor, right, like it says there, 3 ohms. So what I get here is a resistance, sorry, not resistance, what am I trying to say? A current of 2 amps. Okay, so it's just a simple calculation, but you can kind of see how we could use Ohm's law there. All right. So let me say a couple things about currents here. First, current. And we're going to talk way more about this when we get to something called Kirchhoff's Kirchhoff's, I think I say it. Kirchhoff's laws. Okay, so one thing to remember about currents. Applying conservation of energy, or applying conservation of charge. And what I mean conservation of charge is that, you know, charge cannot be created or destroyed in this, even in this wire. However, amount of charge enters the wire should be the same amount of charge leaving the wire. So if I apply that reasoning, right, what it just said, whatever charge enters the wire has to be the same amount of charge leaving the wire. What has to be true because of that is that current for this particular circuit must remain the same throughout the whole circuit. Okay, so anywhere in that circuit, we're going to get a current of 2 amps. Okay, because of conservation of charge. Now I could change the situation a little bit. Let me change the situation. What if I had something like this? Let me draw another circuit diagram. Something like that. Okay, so this will be my voltage, be resistor 1 and resistor 2. So now I have 2 resistors here connected to a battery. This is called a parallel setup, which we're going to talk way more about when we talk about chapter 28. We already discussed parallel connections when we looked at capacitors, and we'll see how we deal with resistors. But I just want to make a subtle point here. So we have current going this way, I, and it hits a junction. We already talked about junctions, right? Junction is when you have a split in the wire. So if we think about that current I is going to be split up. Some of the current is going to go towards resistor 2, call this I1. Some of the current is going to go to resistor 1. I don't know why I called it I1. Maybe I should just call it I2 since it's going to resistor 2. And then we have I1 going this way. Okay, so it's going to split, right? And this is going to be true for any time you have a junction that current splits up. If I apply the same principle of what I had down on the left side of the screen there, that because of conservation of charge, current is going to remain the same throughout the whole circuit. Apply that principle here. At that junction, whatever current I have going into that junction is going to equal the current coming out of that junction. Okay, so for this case, the current going in, I'm talking about this current right here. Now that current's going in. That current is going to be split into I2 and I1, but the total current coming out should equal the total current going in. So that is how we get this relationship here. Your current going in equals your current going out. Okay, so that's just directly from applying Kirchhoff's, applying conservation of charge, and I could write it this way. If you add all the currents going into a junction, that should equal all the currents coming out of the junction. Okay. All right. So we'll talk more about Kirchhoff's laws in the future. All right, let me know if you guys have any questions. Just want to make sure you guys are with me. Like, yeah, so as an examples we've seen here, it's always going to be going, would that be clockwise, right? But if I put the battery here, that's going to be a counterclockwise direction. So I think, don't think of it as current is always going clockwise or always going counterclockwise. You'll be a lot safer and you can apply it to a lot more situations if you know that the current always goes from a higher voltage to a lower voltage. Okay, it always comes out the positive and goes towards the negative. We're looking at the flow of positive charge. Now, there is no actual flow of positive charges. Protons aren't moving freely through conductors. So you could think of current as just going the opposite direction of electrons. Now that doesn't change the physics. Interestingly enough, that you get the same results whether you look at the flow of electrons or the flow of positive charges. You get the same physics, the same conclusions. But yeah, what we're looking at here in the blue is the flow of. It's just think about it this way. We're just looking at the opposite direction of electrons. That's what we're looking at there. And I don't know, it's tricky. Why we got stuck with some I think it's a kind of cool little lesson there about having conclusions without proving it, and now we're kind of stuck with that. Every single, it's normalized, it's standardized, right? The flow of current, even though we know charges don't actually move that direction. All right. Does the second junction do anything to I? Let me go back. So this junction here, right here. So this junction, you have I1 going in, I2 going in, and they combine together to give you I back. Okay, so we do get the current that we had before coming back this way. This would be I. So, and that's what that second junction does. It combines the I1 and I2 back together again, and then you get your original current from the battery. But beyond that, I don't know what else. It doesn't really do that anything else. Okay. All right. So I hope I answered your question there. So let's do an example with maybe requires a little bit more thinking than the ones we've been doing. So I have 2 examples to do, and then we'll be done with chapter 27. Okay, so here's my example. Let me draw the circuit diagram, and then I'll write out the problem. So here's how the circuit diagram looks like. Okay, I'll call this this is I'll just call this R. I'll call these V's here, voltage. These are 2 identical batteries, so they're both V's. And we have, let me put that. I going here, and the same current going here. All right, so there's my circuit diagram. Let me write out the problem so I could give you some context here. 2 resistors are connected to the battery, to 2 batteries, shown below. It's a little bit bigger. All right, both resistors have the same current. Well, actually, these 2 resistors are not the same. So 2 unequal resistors, or I should say, just put it unequal, I guess. That's not the right word though. There's another word that I'm blanking out, but these are 2 different resistors. Maybe I should put that rather than unequal. So 2 different resistors. They have different resistance. So both resistors have the same current flowing through them. How does resistor 1 compare to resistor 2? Okay, so I'll number these. So resistor 1 is down here, and resistor 2 is up here. Okay, so let's think about this in terms of voltage. Okay, so I'm going to just focus in on R1 for now. So R1 has so this is let me get my there. So you have a battery here, starts at 0 volts. The battery increases the voltage to V. You keep going, all this wire is at V, right? The voltage is whatever V is, 5 volts, whatever number it is. So all this wire here is the same voltage. And then we get to another wire, or sorry, another battery, and that battery increases your voltage again. So it increases by another V. So all this wire is at 2V. Okay, so say it one more time. You have this battery, increases your voltage from 0 to V. So all this wire here is at a voltage of V. And a battery increases the voltage by another V. So all the wire here is at 2V. Okay, so let me write that here. We know the voltage here. Anywhere in this section of the wire, that's going to be at V. And anywhere in this section, let me do that. Let me do that a different color. So anywhere in this section, you have a voltage of 2V. What about down here? What's going to be the voltage here? So all these wires are touching. If all these wires are touching, they're all going to have the same voltage. What voltage is that going to be at? So what we should, yeah, exactly. So this would be 0 volts here. Okay. All right, so that kind of gives you an idea of the voltage difference for the R1 and R2. Right, so R1, it goes from V to 0, and R2 goes to 2V to 0. And they have the same current. Okay, so I could do a couple things with this information. Let's go to Ohm's law, right? Ohm's law is this. So focusing on, let me say, for the current going through I1, resistor 1, is the same current going through resistor 2. All right, that's what that equation tells me. And so I'm going to use Ohm's law to make a substitution here for I1. Well, what's a voltage going across I1 or R1? It's just V. So V over R. And same thing for I2. I2, you know, it use Ohm's law as voltage over resistance, but for R2, as you can see in the picture there, that's a voltage drop of 2V. So it's going to be 2V over R2. I forgot to put my R1 there. Okay, so that sets us up, right? That ratio allows us to find what that resistance is. So let me see here. So it says, how does resistor 1 compare to resistor 2? I just do a little bit of algebra. We can see that resistor 2, come on, equals 2 times the resistance of 1. Okay, which should make sense, right? If they're to have the same current, I, resistor 2 has double the voltage. Right, so if we look right here, resistor 2, 2V to 0. In order to have the same current, but double the voltage, you're going to have double that resistance. Right, so more voltage usually means more current, but because this current and this current are the same, that more voltage has to be countered by double the resistance. All right, so there we go. We answered that question. A little bit of thinking there, and I think it's helpful to kind of draw these colors as far as seeing what happens to voltage here. I think it's going to become helpful in chapter 28 as well. Okay, but any questions there? Okay, how do we know the bigger one is 2V? Okay, so it's all about what the battery actually does, right? So if let me see. So go right here, right here. Come on. Okay, so let me start down here then. So with a circuit, and this is true for in general with potential, you could choose your 0 to be wherever you want. Same thing with the circuit. You could choose your 0 voltage to be anywhere you want. I usually like to choose my 0 voltage to be right before I get into my batteries, right? So here. So I'm choosing this to be 0 volts, which means all this wire is going to be 0 volts, right? This whole, because one of the things we talked about with conductors is that if conductors are connected together, they're going to have the same voltage. Okay, that's something we talked about a little while back. I think it was in chapter 26. Okay, so all these have the same voltage, right? Because they're connected together. When you get to a battery, the purpose of a battery is to increase your voltage. Okay, so we start at 0. That battery increases your voltage to V. Okay, so now we're at V for this whole wire. And then we get to another battery. Well, it's the same thing. That battery is going to increase your voltage now to 2V, right? Because we went from V plus V, right? We're adding another voltage there. Now we get 2V. Okay, so now this whole wire is set to 2 volts here, or 2V, whatever that V is. Okay, cool. Okay, so let's do one more example. Okay, this example is a little bit on the harder side, but I think we're up for it. All right, so let's see here. Let me go back to my PowerPoint. Okay, so I want to do this example with this machine. I don't know if you guys have used it before, but I used something like it. You know, before all the gyms closed down, I put my hands on these kind of metal holders, and then I also had to go barefoot and put my feet on these metal contacts. And what that did is it shot a current through my body, and from analyzing the current is able to tell you how much body fat it has. So I'm not going to share that particular information with you, but it's kind of interesting how it works. It shoots a small current through your body, and depending on how much fat you have, that's going to give it a different resistance, and that different resistance is going to affect how much current it could actually send through your body. So by analyzing how much current goes through your body, you can get an idea of how much body fat you have. Now, of course, it's not perfect, especially a device like this. It doesn't go through your whole body; it goes through your arms. It makes estimations and ratios, estimates ratios for how much fat you have on your arm to how much fat you would have on your torso and your legs. So they're not perfect, but still an interesting idea that you could shoot current through your body and analyze that current and get an idea of how much fat you have. So I wanted to do an example with that. And so here's this example. Okay, and it's going to take a little bit of work, but I think we could do it. Okay, so a device to measure body fat sends a current through the upper arm. For a particular person, that current is 0.87 milliamps. And we get that current when that thing that the lady was holding in the previous picture is recorded when a 0.60 volts is applied. Okay, so we have our voltage and we have the total current. Right? The total current is 0.87 amps. The person's arm is 25 centimeters long and has a diameter of 8 centimeters. Resistivity of the fat tissue is, I can't read it, something's covering it, 25 ohm meters, and the resistivity of muscle tissue is 13 ohm meters. What is the percentage of fat tissue? All right, a lot of information there. We're going to break it down, and circuit diagrams are particularly helpful here. All right, so let me draw this out. Essentially, what we have here is a circuit, right? So I'm going to have a battery. That battery is my 0.60 volts. Okay, so I have a battery that's providing this voltage, and that's weird. A little bump on my screen. Well, it's just dirty. Okay, and that's going to go to your arm. So you can see how the problem gave us the arm. The person's arm is 25 centimeters long and has a diameter. So that sounds like a cylinder. So I'm just going to draw this as a cylinder here. Okay, so this is the arm. Right. And we know how much current is going to this. 0.87 milliamps. Okay, so that's essentially that's what the situation is. Right? We have a voltage applied to an arm. It tells us how much current this voltage source is providing, right? The 0.87 milliamps. Now, we're also given this resistivity, fat tissue, and resistivity of muscle tissue. It's important to note, because I see it happen all the time, that resistivity is not the same thing as muscle. Oh, sorry, no, let me repeat that again. Resistivity is not the same thing as resistance. Those are two separate things. They are related, right? We have our equation. Okay, that's our equation. Resistivity times length divided by the area, that gives you resistance, right? My resistance there. All right, so in this picture in the arm here, when current goes to the arm, it has a choice to make, or it's going to be split up, right? Some of it is going to go to the fat. Some of the current is going to go through the fat. Some of the current is going to go through the muscle. Okay, so it might look something. I'm going to draw it kind of like a pie graph here. So we'll be we'll write this in a kind of optimistic kind of way that this part here would be the muscle. So I'm gonna call it RM, resistance from the muscle, and then over here, resistance from fat. I could do that a little better. All right, so so if we're looking at this, we essentially have two resistors there, right? Muscle resistor and the fat resistor. And I think it would be more helpful to redraw this circuit, not so much with the cylinder, but kind of like a typical circuit diagram. Something like that. So you have your voltage, you have your resistor, and this will be your muscle resistor, and this will be your fat resistor. And we have a junction there, and we know what happens to junctions, right? If we have a junction right here, we got current coming in. This will be the 0.87 milliamps, and that current splits I1 and I2. Or I could call it RF for the fat, and I could call it RM for the muscle. Okay, and like I said before, we know that equation for resistance. Okay. All right, so before we jump in and I start plugging in numbers and doing all that, a couple questions for you guys. What is a voltage across RM? So what we talked about before is that anywhere, you know, these wires all have, this is all erasing my dots here. Yeah, I don't like PowerPoint too much. Okay, so anywhere along this wire here, right? All this wire is in contact, and we said when you have wires in contact, they have this. You have the same voltage throughout the wires. Okay, so all this in the red is a 0.60 volts, and we said that on the bottom here, you know, they're all going to be the same voltage. Oh, let's do this little circles. Okay, same voltage there, and that's going to be at 0 volts. Okay, so RM and RF, yeah, they do have the same voltage, right? You can see that for both cases, it starts at 0.6 volts, goes down to 0, right? 0.6 volts goes down to 0. Okay, so RM and RF have the same current. Oh, sorry, no, they don't have the same current. No, take that back. But they do have the same voltage. Okay, so that's going to be important as we put numbers together. Okay, so we know that, and we know we can find resistance through this. Okay, so let's go to the whiteboard and finish off this problem. Okay, so let's start by finding RM and RF. So RM, resistance of the muscle, we could find it through this equation. Resistivity of the muscle, L over A. And same thing with RF. Resistivity of the fat, L over A. Oh, remember the picture I drew on the other slide? I drew something like this. This was supposed to represent your arm. And it said from here to here, right? That was RF. And over here, this is RM. And of course, this was length. Okay, so I drew it like that. And that should give you a hint. about this about how we're going to approach this equation. There's different areas, right? Muscle is going to have its own area, and fat is going to have its own area, right? I hope you see that from the picture, right? That your whole arm isn't purely muscle or isn't purely fat. A percentage of that area is muscle, and a percentage of that area is fat. Okay, so I need to use that in my equation here. So let's see, I'm going to use that percentage. So, okay, maybe I could do a percentage of the total area. So let me try this. So resistivity of the muscle times length over so for RM, I'm gonna say it's some percentage of the area. I guess I could call that X. So X times A, which would be the area of your arm. So X is my percentage. Let me make a little note there. That's the total area of the arm. Okay, I hope that makes sense there. It makes sense to me. I know, but that's not. I want to make sure it makes sense to you guys. So area of the muscle, the whole arm is not muscle. Okay, good, thanks. So we're looking at a percent of the muscle times whatever that percentage is, whatever your body percentage of your muscle is, times the area of your arm. Okay, so and we're gonna do the same thing over here. Wait. If I call X a percent of muscle, I can't use X for the percent of fat. So I guess, let's see. If I assume that muscle and fat are the only two things we're taking into account, right? Whatever percent, like let's say your percent of your muscle was, I don't know, 60%. Then the percent of fat would have to be 40%, right? So we know they add up to 100. Your percentage of fat and the percentage of muscle. So I could just do this then. 1 minus X. Right, assuming X to be a decimal. Okay, so yeah, like I said, the 1 minus X would just be it's not complementary, but the leftover, right, of whatever is not muscle, we're going to assume to be fat. And that's where the 1 minus X comes from. So again, if muscle was like 70%, then 1 minus 70 or 1 minus 0.7 will give you the 30%. Right? It will give you what's left over. Okay, so I think we have all those numbers, right? For resistance of the muscle. Okay, so let's plug in some numbers. I forgot my numbers. So resistivity of the muscle was resistivity of muscle was 13. That's ohm meters. Resistivity or length of the arm was length of the arm 25 centimeters. So 0.25 divided by X, which we don't know, times area, which is going to be pi r squared, because we're taking it to be a cylinder. And what was the radius? The radius, I have it down as 8 centimeters, or it would be 4 centimeters. Okay, for the fat, you get 25. Just make sure it's 25. Ohm meters. Length is also 0.25. Then I have 1 minus X here. Okay, so I'm just plugging in my numbers to my equation for resistance. All right, so I'm going to just do my calculation here. So 13 times 0.25 divided by pi times 0.04 squared. All right, so this gives me, so I'm not doing the x, so 640. So 647 about over x. And the other one, 25 times 0.25 divided by pi times 0.04. 1,243. Okay, so we get resistance here. Okay, so I need to go from this and incorporate my voltage and my current here. I could do, let's go back to the, let's go back here. So if I'm looking at this, I do have this junction, right? I equals IF plus IM, right? Whatever current is going in equals the current coming out. So I could use this right here to see if I could relate my resistance to my voltages. So I think that's the best way to go. I mean, I also know voltages are equal. Maybe we could use that, but then we still don't. We still wouldn't know IM or IF. So yeah, I guess either way, you could start either way. So I'm gonna start with my currents. So I'm gonna use this equation for my current. So let's go back and start and use that. So I total, so this is my currents now. Okay, and then we could use Ohm's law on the right side. So we use Ohm's law, remember Ohm's law, V equals IR. So what I'm going to plug in for my I is V over R. Okay, so this will be my total, my voltage across my muscle over the resistance of my muscle, plus the voltage across my fat over the resistance of the fat. Equals I total. I think I know what I total is, right? It told me 0.87 milliamps. So I don't want to plug in anything on that side because I have a number for that. Right? I don't need to do V over R total or anything like that. I'm just going to keep it because I know my current, my I total current. So I'm just going to keep it as 0.87 milliamps. And I also know my numbers on this side. So the voltage on my muscle side, like we said, is 0.60 volts. And the muscle, well, we calculated up there on the top, 647. Okay, so I kept a couple of extra suffixes there for rounding errors. Times X. Okay, that's my muscle. And for my fat, well, we said fat has the same voltage, right? We said that earlier. So 0.60 volts over, and then the fat. So we got the resistance of fat, 1, 2, 4, 3. And it's a 1 minus X. There we go. So if you look at all those numbers there, we only have one unknown, right, which is X. So it's just a matter of doing the algebra, which I think I'll spare you guys from doing. because I think you should all be able to do that algebra. Solve for x, right? So remember what x is. X is a percent of muscle. So x, let's see. I think I did do the calculations. Huh. I got 0.87, which is kind of weird because that's the same current. So no, I hope that's right. 0.87. So this that means this arm is 87% muscle, and will that be 13% fat? All right, working out that equation. So yeah, it took us a little while to get there, and it was a little bit more challenging to get there, but you know, that I just love algebra is what it came out to be. Let me highlight a couple things that I want you guys to remember though from this. So the way I want you guys to remember, everything was mostly algebra, but one thing to remember is that when you have resistors here in a parallel setup, what we talked about with the red dots, that you're going to have the same voltage difference. So when do we use that idea? Well, we used that when we had our equation back here, right? This V. We used it here and here, right? Otherwise, we wouldn't know what V is. I wouldn't know V for the muscle, and I wouldn't know V for fat. But because they're parallel, and because we did those little dots there, we know they're the same voltage. Okay, so we're able to plug in 0.6 and 0.6. The other thing I want you to remember or take away from this is junctions. All right, we have a junction here. So when we have a junction, that tells us that the current is splitting up. And so without that, I wouldn't have been able to start this. Right, this is where we use that information here. The rest of this example was plugging into calculations. So this equation here, I don't think was too hard to get, right? It's just, we're just applying the equation we saw in lecture. Same thing with this. We had to be a little careful with the x's, but besides that, let's just really plug into lecture. But it was using this equation here for the junctions and then realizing they had the same voltage that was key to solve this problem. We would not have been able to solve this problem otherwise. All right, so that wraps up chapter 27. It took me a little bit longer to do that example than I anticipated, but that's okay. We'll stop here and we'll start chapter 28 in our next class.